Anyway, that was the triple point of water that the temperature is based on, and then the amount of substance. We'll go over this in more detail when we talk about the mole, but basically if you have a certain carbon atom, the mole is how many atoms it would take for the mass on the periodic table to match the mass, I say in real life, they're both in real life, but if I put it on a scale in grams, it's going to match the number on the periodic table. So it's like how many atoms that takes, and it happens to be a really big number, 602, like trillion, something like that. An electric current is gets a little more complicated with those last two. Those are topics you're more likely to study in physics, so I'll leave that for them to give you the details on there. So we'll start with length. Length is a measure of distance, so like how far. The standard unit we're going to use in chem is going to be the meter, and when we're using bigger distances, we're going to use the kilometer, which is 1,000 meters, and we're looking at shorter distances. We're going to use the centimeter, which is 100th of a meter. Second unit we have is mass, and notice the SI unit is the kilogram. I've always wondered why it's not the gram, especially with chemistry. We use the gram more often, but I guess the kilogram is more convenient for everyday objects that you're weighing. Tend to be in the realm of a kilogram. But just be aware, weight is not the same thing as mass. Mass doesn't depend on gravity. So if I have a certain amount of mass in my body, I'm going to have that mass on my body whether I'm here at the top of a mountain or on another planet. Exactly. The weight is what changes. Good. Weight is actually how much that planet is pulling on me. If you ever been to the Science Center, do you know how there's the row of peanut butter jars in front of the planetarium? Might not. It's like one little exhibit. But the Science Center has a bunch of peanut butter jars you can pick up. The heavier ones represent the bigger planets like Jupiter, because the peanut butter jar would weigh more on that planet. But all the peanut butter jars have the same mass of peanut butter in them, theoretically. So with our base units, we can actually create more complicated, more complex units. The area is meters squared. So if I measure my distance from me to the door, and then from the door to the back of the room, I'm measuring two distances to give me a two-dimensional space. So I'm measuring like a square, the area of the floor. And then I can take it one step further, measure from the floor to the ceiling, so I'm in 3 dimensions, and that gives me volume, which is length times width times height, or meters cubed. We've discussed density a little bit. We're going to discuss it a little bit more today. It's a ratio of how much mass I have per volume. Molar mass tells me how much mass I have per amount of something, and molar volume tells me volume per amount of something. And then joule gets really complicated because it's a force times the length, but a force itself is a derived unit. So newtons is what force is measured in. I'll show you how this breaks down. This is more important again in physics, but just so you can see how complex a joule is. So a joule is a newton times a second, or a meter, not a newton second, it's a newton meter. A newton is a mass times an acceleration, so it's a kilogram times a meter per second squared. So this is what a Newton is. So a joule is a kilogram meter squared per second squared. So notice I have a mass in there, I have two lengths in there, and I have two times in there. But that is what a joule is equal to. All you need to know for our purposes is that a joule represents energy. But I just wanted to show you where it comes from. Pressure is another example. Notice pressure is kilograms per meter second squared. We call that pascals. But let's specifically focus on volume. The SI unit for volume would be cubic meters. But a lot of times we also use cubic centimeters. In fact, more often I'd say than not in chemistry, we're going to be doing with cubic centimeters. I don't know if you've ever had those sets when you were in math class, like the little blocks to help you count to 1,000. But those little blocks are about a centimeter in length. So a cube would be a cubic centimeter. You line up 10 of them. You have a row of 10 cubic centimeters. You make 10 rows of 10, and then you have these squares of 100 cubic centimeters, and then you stack those up and you get 10 of those. Eventually you have 1,000 little cubic centimeters. That would represent a liter. A liter is not a SI unit, it's just kind of a definition of 1,000 cubic centimeters. Because it's a lot easier, a liter is a lot easier to say than cubic meters. But there's 1,000 little centimeter blocks in there that make up a liter. And another important thing we want to note, a relationship here, a milliliter is the same thing as a cubic centimeter. So if I have a cubic centimeter of something, I know that I also have a milliliter. One note for when we're in lab on how to measure liquids. A lot of times the surface of a liquid curves in a graduated cylinder. In fact, pretty much all the time. And most of the time we're measuring water anyway, so we have to be aware that there's going to be this thing called a meniscus because the water curves up. It tends to attach to the sides of the container. So just the standard way we measure volume is we're going to look at the bottom of that meniscus. So in this case, you see it's at about 9.5 milliliters in that graduated cylinder. So we're not really going to deal with mercury, but mercury does have a meniscus that curves up because it doesn't have those adhesive properties water has. So we would measure, in that case, we would measure at the top of the meniscus and just kind of go across here and see what it pen kind of glitched out, but we would just measure across and see what the top of the meniscus says. So finally, we're going to end with density here. Density is the ratio of mass per volume, so mass divided by volume. It's an algebraic equation. Density equals mass divided by volume, or D equals M over V. A lot of people like to see it in a triangle form. If I put mass on top, and then D and V on the bottom. What that does for me is if I cover up M with my hand, then that tells me to find mass, I'm going to multiply density times volume. If I cover up D with my hand, I can find density by dividing mass and volume. And then if I cover V with my hand, I can find volume by taking mass divided by density. It's all just simple algebra, but people like it when they see it in the nice little triangular form. These three should be up here, but the derived SI unit is kilograms per cubic meter. But we also use grams per cubic centimeter. I would say we use this more often. And then note that's the same as a gram per milliliter. And we talked about this last chapter. Density is an intensive property. It's characteristic to the substance. So I can say copper has a density of blank. Aluminum has a density of blank. That applies for any substance that's pure. We can relate to it by its density. And that's a clue that can help us identify a substance. For instance, I might have a clear liquid that has a density of 1.59, but I'm not just going to assume it's sucrose because it has that density. I'm going to look at other physical properties as well. I'll think, I know sucrose is a white solid, so am I sure that this clear liquid is sucrose? It's probably a solution of something else. A couple key things to look at. Notice water is very close to 1 gram per milliliter, meaning if I have a gram of water, I know I have a milliliter. Vice versa, if I have a milliliter of water, I know I have a gram at 20 degrees Celsius. Ice, when we freeze it, notice it's at a colder temperature. But when we freeze ice, notice how it has a less density than water. So that's why ice floats on water. Got lead. Lead's very dense metal, 11.3 grams per centimeter cube. Mercury is pretty dense liquid, so those things are going to sink in water. So do one calculation. It shouldn't really hurt our brains too much, I hope. It's just a density problem. They're asking us to calculate the density. So we're going to take the mass divided by the volume. In this case, the mass is 8.4 grams. The volume is 3.1 cubic centimeters. When I take those out, I get a longer number on my calculator. So if I look at my calculator here, I guess there's an issue with that coming up. But I'll just use Google here. 8.4 divided by 3.1. Notice I get this large number, 2.7096. I don't really want to write that whole thing out as my answer. So what I'm going to do, and we're going to learn more about this, more rules about this later. But notice how 3.1 and 8.4, they both have 2 digits. So kind of a good rule of thumb for now is just round off my answer to 2 digits. So instead of writing that 2.706 whatever, I'm just going to write 2.7 grams per cubic centimeter. So I actually picked a multiple choice that gives me the same answer, not on purpose, but it gives me an opportunity to talk about this. What happens if I have, so I'm trying to find the density of it's mass divided by volume. So 45.65 grams over 16.9 cubic centimeters. Notice here again, I'm going to get that long string of numbers, but I'm going to write 2.7. I have to decide, is it 2.7 or 2.70? I'm going to write 2.70 grams per cubic centimeters. Anybody have any ideas why I might do that?